How is it, guys? So today we are going to understand geometric series and sequences. Okay. So let's again start with the basic maybe. What is a sequence? A sequence is just a given list of numbers. Okay. And I'm going to explain what geometric means and how is it different from arithmetic sequences and what formulas do we have and how we go about solving the questions in our exams. So first we are going to start with geometric sequences. What is a geometric sequence? It's a just general term, a list of the terms that has been given to us. So I'm going to show you a list of terms, and can you decide or can you look at the pattern and tell me what pattern you see in these? So this is a geometric series that we have. If you will look at this pattern, and if you try to look at the pattern we have in this sequence, what comes to mind? These terms are getting increased very fast. So what does it look like? Okay. If you will look, each next term in this series is just a multiplication by 3. So if we multiply this and this, we will get 3. See? This and this is just a multiplication of 3. So on and so forth and so forth. Okay. So now we are going to talk about the formula and the general terms. You can write this down here. Generally in these formulas, we have n, which represents the position. It represents what position in the sequence do we have. So the general formula that we have is going to be based on T of n, where n represents position. And it's always a whole number, of course, because the position cannot be a fraction. There cannot be something at 2.5 position, right? If we talk about A represents the first term in the series or the sequence, whatever we are dealing with. Right now we are dealing with sequences. So A represents the first term in the sequence. So if I go, it's for the first term in sequence. In this case, our A is 5. And what is our R? R is going to be 15 by 5. 50. Second term divided by the first term, which is 3. Okay. What is R? Okay. So R in the case of arithmetic series, we had D, which was the common difference. Each term was derived by adding that term to the previous term. In case of geometric sequences, we have common ratio, which is written as R. So R is our common ratio. And it is different because R is generally derived by dividing T of n plus 1 divided by T of n. Take any term and divide it by the term before it. And then if the ratio is constant, then we know we have a geometric sequence or a series on our hands. Based on this, we are going to derive a general formula for our geometric sequences. So let's see the general formula. So here in this sequence, if we see, the first term is always going to be constant, right? The first term hasn't been multiplied by the common ratio yet. So it is written as it is. And then for the subsequent terms, we just take the position, we subtract the position, and then we multiply it by the common ratio. So in this sequence, if you will see, we can write this sequence as something like 5, 5 multiplied by 3, right? And we can write 45 as 5 multiplied by 3 multiplied by 3. 9 5s are 45. So we have 45 here. So there's a way that we can represent 3 multiplication of 3 by position. We are going to use power for that. And that's why we have the term as T of n is equal to a multiplied by common ratio power n minus 1. So for the first position, the n is going to be 0 and it is not going to be multiplied yet. T3 is equal to 5.3 square is equal to 45 matches. Yeah, so we can do a sanity check for our formula if it is correct or not. And here it looks correct. Let me put this here so we can use it again and again. So our Tn can be used in both directions. What I mean by that is, if we have our formula for a given term in a sequence, we can use it both ways. If we know the value of a term, we can determine what position that terms appear in. So if we have a sequence, let's say 2, 4, 8, 16 and so on. And then if we want to determine on what position 1, 2, 4 might appear, on what position 5, 1, 2 might appear, what any value given to us appears at what position, we can use this formula. Or if we are given the first term and the position we want to know and the common ratio, then we can determine what the value at that particular position in our sequence is going to be. Here is a sequence that has been given to us, right? This is a sequence that has been given to us. And now using this sequence, we want to drive the values and we want to drive the general formula, Tn. Okay, for Tn, what will we require? We will require the first term, which is 96, and we will need to find the common ratio. What is the common ratio of this series? If you want to try this, try it yourself. Try dividing any term by the term before it, and that will be our common ratio. We know the value of a. Based on that, you can try to drive the general formula for this sequence. Okay, our a is 96 and our r is 1 by 2. 48 divided by 96 is 1 by 2. 24 divided by 48 is 1 by 2. 12 divided by 24 is also 1 by 2. And if you notice here, the common ratio is in fraction, which is a totally valid option. When our common ratio is in fraction and that fraction is smaller than 1, then our series keeps going down and down and down and down and down. What we are doing in this sequence or series is we are constantly taking each term and making it half and half and half and half. So this can go on. So now I want us to drive this general formula and use it to find T of n. Okay, let's say we want to find T of 10. How will we do that? We will take 96, 1 by 2 and power of 9, right? N minus 1 is 9, the position here is 10, and we will just solve this, which will come out to be 96 by 2 to the power 9 is 512, and then we see T of 10 is going to be 3 by 16. Yeah, keep in mind the position n is never going to be a fraction. The value of n can never be a fraction, whereas the value of Tn of any given term at any position can be a fraction. R can also be a fraction. A can also be a fraction, but the position in the sequence is never going to be a fraction. We can use this type of formula to find the position also. Let's say it has been given to us that 3 by 4. What position 3 by 4 in? Okay, so the question which will be given to us is what position 3 by 64 is going to be. So the question that will give us, it will tell us that, hey, we have a term in this sequence which is 3 by 64 and at what position it occurs. Based on these values, the general formula that we had for T of n was A. Let me substitute the value of A. A is going to be 96 and R is going to be 1 by 2. So this is our Tn, right? The formula for general formula for our sequence is this. It's 96 multiplied by 1 by 2 power of n minus 1. And now it has been given to us what is the value of this. So we will make 3 divided by 64 as T of n. We will substitute it here in this equation. We will take this and we will substitute it here. Into T of n. We are just taking this, substituting it here, and then we get this, right? One by 2, n minus 1, 3 by 64, and we shifted 96 here, and then we get 1 by 2048. 2048 is going to be 2 to the power of 11, value is 2048, which is equal to 1 by 2, and then the value of n is going to be n minus 1 is equal to 11, so the value of n is going to be 12, right? Because 1 by 2 n minus 1 is equal to 1 by 2 11, then we can cancel 1 by 2 out and we can just compare n minus 1 is equal to 11, and from that the value of n is going to be 12. Okay, moving on. One more type of question that we can see in the exams are inserting geometric means. So they have given us the value of A and they have given us the value of T6, and they are saying what are the 6 terms. So the T6 is going to be 2 to 4. We need to find the value of the middle 5 terms. Okay, so how many unknowns are there? Let's try to figure that out for solving this question. Then we will need to determine how many equations we will use with that. So in this, if I take this equation from this question, I know that my value of A is 7, right? My value of A is 7. R is something that is still not known to me. And there is one more thing that I can write using this, which is that my T of 6 is equal to, I can substitute the value of A. I don't know the value of R, but for T of 6, it's going to be 6 minus 1, which is just 5. So can I say this? T of 6 is equal to 7r to the power of 5. And do I know the value of T of 6? Yes, I know that. That's given in the question, which is 2 to 4. So what I can write is T6 is equal to 2 to 4. Two to 4 is equal to 7 r to the power 5, and then we can solve it to find our general term. Let's see that happening. See, 2 to 4 is equal to 7 r to the power of 5. And now we can just say r to the power of 5 is equal to 32. 2 to 4 divided by 7 is 32. So r is equal to 2, because 2 to the power of 5 is 32. So now we have the general formula. Now we have the value of 2. Then what is our t of n going to be? The t of n is going to be 7 c dot, the value of r is equal to 2 to the power of n minus 1. This is our t of n. And using substituting n, we can find our sequences. So for the first term, it's going to be 7. For the second term, 7 multiplied by 2, 7 multiplied by 4, 7 multiplied by 8, and so on. So this is how we can find the terms between. Now, in all of these questions, the first value or the value of a were always given to us. You notice here, the value of a was given to us. In this question, also the value of a was given to us. And now we will see the questions where the value of a is not clearly given to us. Okay, the question is going to say t of 5 is equal to 32. And t of 2 is equal to minus 4. So this is something the question will give us. So the question will tell us that the t2 value is minus 4 and the t5 value is 32. And based on that, we will have to derive the value of a and r in order to form our generalized formula for t of n. So in order to determine t of n, I need to find the value of a and I need to find the value of r. For finding value of a and r, these are two unknowns. So I need two equations to solve it. So t2, can I write t2 as ar based on this formula? Because I have this formula, can I use this to write t2 as a into r to the power of n minus 1? And when I put n is equal to 2, it will just become r. So t of 2 is equal to ar. And in a similar way, t of 5 is equal to a r to the power of 4. Right? These are the two things that we have now. Now, how are we going to substitute these equations in one another? So what are we going to do is, we are going to divide 2 by 1. We are going to divide this by one another. We are going to divide 2 by 1. And then when we divide, a is gonna cancel out. And this is going to become the power of 3. This is going to become 3, right? R3 is equal to 34 divided by minus 4. 32 divided by minus 4, which comes out to be minus 8. R to the power of 3 is equal to minus 2. Minus 2 multiplied 3 times is minus 8. We can substitute the value of r into equation 1. We will substitute r into equation 1 and then we will find the value of t2 and we will find the value of a. So a multiplied by minus 2 is equal to minus 4, which will give me a is equal to 2. So now what is my general formula going to be? T of n is going to be, I have the value of a and I have the value of r. 2 into minus 2 to the power n minus 1. Okay. Yeah. One interesting thing I want to show you guys here and I want you guys to notice is that the value of r in our case is negative. So when the value of r is negative, the sequence that we have is going to oscillate. What I mean by oscillate is the sequence that I have is going to go up and down in values. So let's say we have plus values here and we have minus values here. So my sequence for the first term was at 2 and then it went to minus 4 and then it went to plus 8 and then it will go down to minus 16. So you see the values here are going up and down and up. Whenever the value of r is negative, like we have in our case, and we calculate the sequence, for all the even terms, the negative value is going to get cancelled out. So if we multiply minus by minus, the value will get cancelled out. So for all even terms, the value of r is going to be positive. And for all odd terms, the value of r is going to be negative. So our sequence will oscillate between plus and minus and plus and minus values. Okay, so we are going to look at the next type of questions now. These are the type of questions where the expression of the quadratic of the geometric sequence will be given to us in terms of x. So in the questions, it will be given to us that our sequence looks like this. So the first term, the second term, and the third term of the sequence is given to us in terms of x. Okay. Instead of giving us the value of a, r, or anything else, it has been given to us in terms of x. Because we have only one variable, we need only one equation to solve it. If you guys remember, in a similar question in arithmetic sequences, what we did was the common difference, we derived common difference by subtracting this term from this term in case of arithmetic sequences. But in case of geometric sequences, what we are going to do is we are going to use the logic of common ratio and we are going to write this series as we are going to write this sequence in a way so we can derive r from it. Okay. So what is my r? The definition of r is the value of r is going to be 2x minus 6 divided by x minus 6. Right. But this value is also going to be same when I have 5x plus 3 divided by 2x minus 3. Just like in the first example that we have. Every time we are multiplying the next number by a constant number. So if we divide this by this, it's going to be 3. If we divide this by this, it's also going to be 3 because 5 and 3 are going to get cancelled out. So we can use the same thing to say here. 2x minus 6 will be equal to 5x minus 3, 5x plus 3 divided by 2x minus 6. And now if we cross multiply this to this and we cross multiply this to this, both of these are of course equal to r. And if we multiply this and this, then we will get this equation. Right? And if we solve it further, if we take the square of this, which is going to be a square plus 2ab plus b square. It's going to be equal to this. And if we solve this further, then it's this. So if you guys know how to factorize this, then it's easy. And if you don't, I can help you with that. So we have to find two numbers which multiply to 54. And if we add them together, they add to minus 3. And we can take minus 9 and plus 6 as our numbers. And we can then say x minus 9 and x plus 6 is equal to 0. So our x can be 9 and 6. So this is very interesting because we have two solutions for our question. So there are two values of x which can satisfy this. So we have two solutions for our question, and we can use both of these values to figure out all the terms of the sequence. And according to this, we will have two sequences which can satisfy the condition that has been given to us. And if you don't know how to factorize like this, you can always use the formula plus minus b plus minus b square minus 4ac divided by 2a. If you use this formula, you will get the same values. And now we are going to take this given sequence, and we are going to use 9 as the first value, and we are going to substitute it to get the sequences in this. So if I substitute 9 into this, I will get 3, 12, 48, where r is equal to 4. So 12 by 3 is 4. 48 by 12 is also 4. And if we substitute minus 6, we will get 20. In this case, r is 3 by 2. Minus 12, minus 18, minus 27. 27 by 18 is 3 by 2. And same goes for 18 by 12. So because we have two values of x, we will have two formulas for Tn. So the Tn in both the case is going to be, if you guys try to substitute these values into this, what is the value of a? My a value is 3. And the value of r is 4. So this is the Tn in this case. And in this case, the Tn is going to be, the value of r is minus 12. And the value of r is 3 by 2. Right? This is my formula for Tn for given value of x's. And in both the cases, the value of a is also different. So this question had two solutions instead of one. And these questions for geometric are very common, and they have a very similar way of solving these. Okay. Now we are going to move from sequences to series. Up till now, we were only talking about sequences. We were not talking about sum of these numbers. We were only talking about what list elements we have and how we can derive the general Tn formula, how to use the Tn formula, which is a multiplied by r to the power of n minus 1, and so on. But for sequences, this was fine. But now we are going to talk about series, in which we are going to talk about the sum of the numbers. Okay. This is an example of a sequence, and a series is written like this. Yes. Okay. You get more terms now. S of n will represent the sum of first n term. So when I write here S of n, this will represent sum till that position. So what S of n is? S of n represents the sum of the numbers up till that position. For example, S of 3 in this case is going to be sum from here till here. S of n in case of 4, S of 4 is going to be sum of first, second, third, fourth, all of these combined. So this is how we write S of n. Okay. Now we are going to derive the formula for this S of n. So we have a general formula which represents what each value in the sequence should be. Now we are going to derive another formula which tells us what the value of sum in a sequence is going to be. So what is the value if we want to know the sum of first n terms up till any n? What is the generalized formula for that? Okay. So I would recommend watching the arithmetic sequences video first. It's linked in the description up top. Okay, so if you remember how we derived the formula for quadratic series, it was by subtracting and using L as our last term and using that to cancel out all the common difference terms. So when we look at this series, we need to figure out a way so that we can cancel out all of these R terms from here. So just like in quadratic series, we used the same series itself to cancel out all the D terms. We are going to do something similar here. We are going to take this series and we are going to modify it in a way so we can cancel out as many these R terms as we can. So our formula can become easier. Okay, so this is the same series written by multiplying by R both sides. So we multiplied by R, we took this series and we multiplied by R here and here. So here we multiplied it by R and here we took the whole thing and we multiplied the whole thing by R again. And when we do that, what we get is the same series, but each term is shifted to the right a bit. So this becomes essentially AR, this becomes essentially AR, and there will be nothing here. And this becomes essentially AR to the power N. Because it was N minus 1, we multiplied by R, so it will become R to the power N. And now we are going to use this to drive the formula for S of N directly. Okay. So now when we have this R, what I'm going to do is, I'm going to take this second one and I'm going to subtract it from the first one. You see, all the terms in my sequence are now present. And if I take this and if I just subtract it, what will happen? This will cancel out this. This will cancel out this. And so on. So let's see what happens. You see, all of these terms cancelled each other out. We multiplied by minus 1 and we subtracted this into this. We subtracted this from this. And all of these terms, they got cancelled. Now when I do Sn minus Rsn, what I get is just this term and this term. And this is what my final result is. Sn minus R, Sn is equal to A minus A R to the power of N. And now can we take this common? Can we take 1 minus R common out? Can we take Sn common and write it like this, which is equal to, we can also bring out A as the common one. And this is my term. And now my formula of Sn is going to be A 1 minus Rn. A 1 minus R to the power N and 1 minus R. This is what my formula for Sn looks like. Right. But there is one more thing we need to keep in mind here, which is that if my R becomes 1, then 1 minus 1 is equal to 0. And we cannot divide by 0 or our top number will become to infinite. So there is one condition here, R cannot be 1. If R is 1, then this formula will not work and it's not a legal value that we can use in this formula. Okay. So this is our formula for S of N. Now we are going to talk about how we use S of N. When the N is given to us, when A, R and the value of N is given to us, for example, the N is 7, A is 5 and R is 3, then we can just use this formula and we can just substitute the value. So N of 7 will become A 5 multiplied by 1 minus 3 to the power 7 divided by 1 minus 3, 1 minus r. This becomes a very big value. 3 to the power 7 is 2187 divided by minus 2, which becomes 5465. Okay. Now a different variation of question is when we don't know the value of n, but it has been given to us that the sequence starts with 5, the r value is 2, common ratio is 2. And it has been given to us that find for me what position this, how long the series should be so that my value is this. So what we do is we simply take a into r to the power. We just use Tn formula to find out what position this value occurs at. So we can say 2 of n is equal to this. 2 to the power n minus 1 is equal to this. 2 to the power 17 is equal to 18. And then we can say 17 is equal to n minus 1. We will transfer 1 and then we will say n is equal to 18. And if you have to find the sum till 18th, this is going to be the sum. We will use this formula again. Now we have the value of a, we have the value of r, and we have the value of n. Then we will find it. Just in this question, the value of n was not given to us. So the value of a and r was given, and it was given to us that this is the last term of the sequence of the series. And then we will just substitute this formula and we will find our value. Okay, this is another very interesting part, infinite sum and convergence. Okay, so in our arithmetic series, if we have something in plus and it keeps rising and rising and rising, if we continue that till infinity, we will get a very, very, very big number, which we can say is almost equal to infinitely big number. Okay, now we are going to look at infinite sum plus convergence. Okay, so what is infinite sum and what is convergence? If you look at this sequence, the value keeps going down. This is 16, this is 8, this is 4, this is 2, this is 1, and so on. This will be 0.5 and so on and so on. The value will keep going down and down and down. So what I want you guys to realize is, if we look at the sum goes for 16 to 24, which is a very big increase. But then the sum also starts increasing very slowly. From 24, it only goes to 28. So this is 16. The sum of first two terms is only 24. And the sum of first three terms is only 28. And the sum of first four terms is only 30. The sum of first five terms is only going to be 31, which is not very high. So you see, the sum is not increasing so fast. (32). Okay. So now, if we keep on going and going and going, how far do you think, how big do you guys think this is going to get? If we keep going till infinity, if we keep on going till infinity in this series, the total sum is going to be 32. Okay, you might find it hard to believe, or that might be something which is very difficult to imagine. We will add some nice visuals and I will explain you how geometrically and how visually this makes sense. But for now, I want you guys to realize, because the terms of this series are getting very small very fast. We started from 16 and the fifth term is already 1. And if we keep going and going and going, the terms in our sequence or the series will keep on going very small and small and small. This from 1 will go to 0.5, 0.25, 0.125, which is a very small number. And we can take this to infinity. We can keep on doing this for infinitely long time, and the result is going to be 1/2. Okay. We are going to show the visual formulas of how this makes sense and how this might be true and how we can imagine some infinite sum like this to be a total whole number. But here I want you to understand that the value keeps going down. Then we can say sum till infinity can exist. You understand? If the terms or the values or the terms in my sequence keeps going down and down and down, we can sum it up to infinity. So in geometric sequences, infinite sum exists, and that infinite sum can be a real whole number instead of something being infinitely big. This can be a real number. Okay. And how do we decide whether this infinite sum will exist or not? So this is very simple. Only if when the value of r is smaller than 1, the terms will keep on shrinking and an infinite sum will exist. So whether the value of r is whenever the value of r is between minus 1 and 1, an infinite sum can exist. Because the value of r is going to get multiplied with each term of the sequence, and when we multiply it by each term, a lot of terms are going to get really small, and all of them can be summed up to a complete number. Here we look at example, and we will also look at some nice visuals to explain how this might make sense. So what I want you guys to realize is, if the r value was more than 1, then my terms will keep on increasing. So here, if I, for example, if I start with 16 and my r value is 2, this will become 32, and then it will become 64, and so on. So as we go to a very long position, as we go and talk about position at the 100th term or 200th term, that will be very big, and the sum for this will be infinitely big, and it's going to be a very big number which we cannot express. So it doesn't make sense to ask the question there, what will be the sum till infinity? But in the cases when the r is less than 1, an infinite sum can exist for my series. Okay. Okay, and only when the r value is minus 1 and between minus 1 to 1, an infinite sum can exist. Okay, now we are going to look at this formula, and we are going to figure out how we can modify it to include infinite sum series. Okay. Now I have this s of n, which is equal to a 1 minus r to the power n divided by 1 minus r. What is going to be the s of infinity? And this is the sign of infinity, which tells us that we are summing up the whole series up till infinity. Okay. Okay, so I want you to imagine the values, these values. Okay, we have these values. Okay, and if we try to plot them, what we will see? If I take this and if I plot the first value, it's going to be somewhere around 16. That it went to 8, then it went to 4, then it went to 2, and then it went to 1. Okay. This was my value here, this was my value here, this was my value here, this was my value here. So you can clearly see that this value keeps going down. Now, because we are dealing with mathematics, it's hard to imagine infinity, but in mathematical plane, there is a point on this graph that is infinite, right? And we can keep on going very far away. And our terms will keep on getting smaller and smaller. But after a point, they will become so small that they are almost equivalent to 0. So for this sequence, we have this formula for S of n, and we are going to try to recreate the T of n formula for this, okay? So for this series, the T of n is going to be a plus a16 plus r to the power of n minus 1, and our r is 1 by 2, right? This is our T of n. And now if you look at this graph, our fifth term is 1, right? And as we keep going and going and going, the value of T of n is going to get very, 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 very small. But in mathematics, if we go up till infinity, the value will actually become 0, because we are taking a really, really small term and then making it even half. Okay, so let's imagine 1 to the power of 6. 1 by 2 to the power of 6. 1 by 2 to the power of 6 is a very small number. It's this number. It's 0.01562. And let's imagine 1 by 2 to the power of 9. And this is a very, very, very small number. You see, just from going from power 6 to power 9, this number reduces very fast. If you guys can find a calculator, or you can find an online calculator and calculate this yourself. But this is very important to understand intuitively. How can we sum up something to infinity? Because if the values are going down really fast, when we reach infinity, the value is going to be almost 0. You see, the value of 1 by 2 to the power of 9 is already 3 zeros. But if here we go to a very, very big value, the real value will become 0.00004 or something. So this is a very small value which till infinity can actually become 0. So you can see when we sum this up to infinity, r to the power of n can actually become 0. Okay. This r will remain as it is because it still is a subsequent value. And what we did was we just took this formula. And for infinity, when the r value was really small, then when we said r to the power of infinity, we can make it almost 0. Because it's going to be a very small number which is almost like 0.0000000 for a very long time, and then some number which doesn't even make sense to subtract from 1. So we can round it off and we can say the formula for S infinity is this, which will become something like A1 minus R. So this is the simplified formula that we have for S of infinity, A1 minus R. But this will only happen when value of R is from minus 1 till 1. Okay. So I hope this formula makes sense, and then we can talk. I can show you guys some nice visuals and explain to you how geometric sum till infinity might make sense visually. Okay, one last thing. Before, when I was starting this series, I told you that if we sum this up to infinity, the answer will be 32. And now we can use this formula to actually test it out. So we can copy this and we can move it here and we can see. Based on this series, our value of A was 16 and the value of R was 1 by 2. And if we substitute into this formula, the answer we get is 32, which I told you in the before. So now we know how it was 32 and what formula we used, and we can see the visuals and decide and understand how it might make sense for an finite geometric series to actually sum up to a complete whole number. Now we are going to look at this example, this interactive example, which can help us visualize what a geometric sequence or a series looks like. And later on, we will also see something for different common ratios. But here we are going to see common ratios which are bigger than 1. So here we are only talking about the cases where my R is greater than 1. Where my R is always greater than 1, or my R is less than -1. Say my common ratio is 1 and my first term is 1. Then what my sequence will look like? It will look something like this. The first sequence is going to be 1, and also see the height here represents the actual value. So this is 1. The second term is also going to be 1. The third term is also going to be 1. 1, 1, 1, 1, 1, 1, 1, right? Okay. Let's say my common ratio now is 2 and my starting terms is only 1. Still, starting term is still 1. Then what my sequence is going to be like? S of 1 is equal to 1. Then I will have 2, because 1 multiplied by 2 will be 2 and the total sum will be 3, but this is the length 2 and this length is twice the length of this section. You see, the length of this height actually represents how big the value is. So the first value was 2, the second term in the sequence was 2, the first term in the sequence was 1, and the third term in the sequence is going to be 4. See, this is 4, this is 2, this is 1, and you can see how fast the values increase in case of a geometric sequence or a series. When my common ratio is more than 1, the values can increase really fast. You see, the values can actually go up very high. We can visualize this in scales of 3, and then it's going to 1 was multiplied by 3, then we had 3 branches and it was again multiplied by 3, and so on, and then this will go on to be very high, very fast. You can see how fast it grows in case of higher common ratios. You see. Okay, now who can tell me what will happen when we change the first term to be 2 instead of 1? Now the starting term was already 2. Now what we will have? We will have 2 trees that are growing really fast. In case of 2, we will have, instead of 1 tree, we will have 2 trees that are going really fast. Do you see? Only at 6th term it is 64 and the sum is already 126. Okay. Yeah. If you want to play around with this experiment, this is present on SyntroLearn. You can visit from the link in the description and you can play around with it in resources. Now we are going to look at examples where R is less than 1 in my case of geometric series or sequences. When my R is less than 1, there are very interesting visual examples where we can imagine how summing a series up till infinity gave us a finite result. Because sometimes when we look at the formulas or something, this looks scary. This looks like we have infinity and we are summing things up to infinity, and can be confusing understanding how something can be summed up to infinity and still be a finite number. So that is why we have this example to help us visualize. Okay, so in this case the R is 1 by 2 and let's say our starting term is 1. We assume that. So what is happening is we have this triangle whose area is 1. This triangle's complete area is 1. Okay. And what I can use this sequence to represent is, I took this triangle and I divided it from the middle. Then this is half, right? If the whole area was 1 and we divided in the middle, we can just use symmetry to think about it. And we can say this area is going to be 1. And this is the first term of my sequence, of my series. This is the first term of my series, which is 1 by 2. And the second term is 1 by 4. The third term is 1 by 8. So what I essentially did was, I took this whole triangle and I divided it into half. And then it was 1 by 2. And then what I did was, I took the whole triangle again, which is this much. And I again divided it by half, but from this side. And then this was 1 by 4. Then I took this triangle and I again divided it by half. Then the area will be 1 by 8. And this is my third term of the sequence, which is amazing to think about. Okay. And now we can see how it will happen that the infinite sum for this comes out to be 1. You see, this is how we can see how this might happen. Okay, and let's grab our formula for sum of infinity. The infinite sum in this case is s of infinity is equal to a divided by 1 minus r. And if we go here and we write on our formula that s of infinity is equal to a divided by 1 minus r, right? Please mind my writing here. So might be difficult, but yeah, just bear with me for some moments. So this is what my formula is, and if I substitute the values here, my a value is 1 by 2 and my 1 minus r will be 1 by 2 divided by 1 minus 1 by 2, right, which comes out to be 1 by 2 divided by 1 by 2. Both of them will cancel out and my result will be 1. So my formula tells me the result will be 1. And then here we can imagine how we got to the 1. So every time we are taking the triangle and we are dividing it into half. We are dividing it into half. We are dividing it into half again and again and again. So we are taking this triangle, then dividing it into half. Then we got this triangle, this triangle. What we are going to do is again divide it into half. And these are the sequences that I have. Okay. And how, when we are multiplying it to infinity, these terms can go on, right? These terms can just go on. So we can have these terms going on for a very long time and they would still multiply to be infinity. You see, this is the most interesting bit here. Okay. Now let's look at another one with r is equal to 1 by 3. Okay, in this example, what my sequence represents is 1 by 3, 1 by 9, 1 by 27, 1 by 81. Okay, let's do something first, which is use our s of infinity formula. And let's solve it. So our a is 1 by 3 divided by 1 minus, if we divide 1 by 9 by 1 by 3, then we will get 1 by 3. Right? This is my common ratio and this is my first term. So what will be my s of infinity? It will be 1 by 3 by 1 by 2 by 2 by 3. And the 3's will cancel out and my result will be 1 by 2. Okay, so this is my result. My formula verifies it that I can find this to be 1 by 2. Now we can see visually how we will actually visualize it and how it actually makes sense that this becomes 1 by 2. So I have a triangle here. I have a square here, sorry. And in the square, what I'm going to do is I'm going to say the area of the square is 1. This side is 1 and this side is 1. Then of course my area is also 1. And I am going to divide it into 3 equal parts. I divided my square into 3 equal parts and I can say area of this part is 1 by 3, right? Which is my first term. Then I will take this whole rectangle. I will take this rectangle and I will say, because the area of this was 1 by 3, this whole section's area was 1 by 3. Can I say this whole section's area will also be 1 by 3? This top rectangle will also be 1 by 3 because it's equal, right? Because of symmetry. We don't need to think about formulas, we can just think about symmetry. And then I took this whole rectangle. Then I took this rectangle and I divided it. This was equal to 1 by 3. And I divided it again into 3 equal parts. Here and here. And now this area will be 1 by 9, right? This is my second term. And so on. So now using the same logic, we can say all of these blocks are 1 by 9. And I'm taking this, so this block is also 1/9 the area, right? I can divide this into this. And this is 1/9 the area, and I'm again dividing it by 3, which is my third term, 1 by 27. So this is my third term. And I'm summing all of this up to infinity, right? So this can go on up to infinity. This sequence or series can go on up to infinity. We can keep getting smaller and smaller and smaller, and we can just keep on dividing our polygon into smaller and smaller numbers, right? But what I want to understand is at any level, if you will see, the remaining area is equal to the other area. You see? So at any angle, if I look at it, the remaining area, this area which remains, this area which is remaining in the big triangle is always equal to the area that was shaded. When I sum this up, so all the smaller parts of this sequence will only be able to make the area which is half. And as we established at the start that the whole square has the area of 1, then the half of that will be 1 by 2. So this is a way we can imagine how my infinite geometric series can sum up to be a fraction that makes a lot of sense, and it can have a number that is finite and can represent the sum of an infinite series. You can look at one more example for this. Here my series is 1 by 4th, okay? My common ratio is 1 by 4. So I have this triangle, let's say. And I'm dividing it into 4 equal triangles. This triangle, imagine this as one triangle and another triangle and a triangle here and a triangle here. If you will just look at by symmetry, this triangle is equal to this triangle and this one is equal to this one. So all 4 of them are equal. And that's why I can say that this area is 1/4 the area of the total triangle. And my total triangle area was 1. Using symmetry, I can say that this whole portion and this whole portion and this whole portion, this whole portion and this whole portion are equal. And that's why I'm saying this area is 1 by 4. And now what I have is 1 by 16. So now this triangle was also 1 by 4th. And then we divided it into 4 equal areas. And then what we get is 1 by 16, which is the second term of my series or the sequence. And we can keep doing this till infinity. You see, we can keep on doing this till infinity. 1 by 26 and so on and so on and so on. And my sequence just continues. But I'm saying here that my total area is equal to 1 by 3. Okay. How do I get that? I again use the formula. I use the S of infinity formula. And I say my A is 1 by 4. Which is divided by 1 minus 1 by 4. Which is also my common ratio. So this will come out to be 1 by 4 by 3 by 4, which will come out to be 1 by 3. Okay, This is the same value that we have here. So our formula is correct. Now we are going to see how it visually makes sense that this infinite series or sequence sums up to be 1 by 3. Okay. I divided my triangle into 4 equal parts. But now what I'm saying is, because for this, all of these, the remaining area, this area which is in red and this area which is in blue is equal to the area which I have here. So I'm saying that the area of red, this section, if we look at it by row now, if we look at these blocks now, and if we look at them, then we can say on each level, these are 3 triangles that I have that are equal. Just based on symmetry, imagine that these triangles are equal. Because this is equal to this and equal to this, which you have already established. And on each level, the same thing is happening. On each level, these triangles are equal. So on each level, I'm taking 1/3 the area of the total triangle. And I'm summing this up to infinity. You see? So on each level, I'm just taking the area of this triangle in the middle. And I'm just summing this up to infinity. You see? On each level, I'm just taking the triangle here, here, here. And I'm just summing it up. And then I'm saying, because this is just 1/3 the area on each level, my total sum is going to be 1 by 3. Yes. I hope these examples help and make the concept more clear and give you a more of interest of what these formulas represent and how amazing it is that we can represent something like this with a very simple formula which is very general and works on any sequence and series. Now we need to look at one more type of examples that are left to us. Using the S of infinity and the concept we learned here, that our sum of a series converges to a finite number when the R value is -1 to 1. When the value of R is between -1 to 1, the sum will converge. This is the formula that we just derived, we proved, we saw it visually, and the questions that we can have in the exam are, it will be given to us that this is a series. This is a geometric series. Now it will be asked of us that for what values of k does my values converge? That means a finite sum exists for this series or sequence for what values of k. What values of k will get me to a finite sum? And as we just learned, the R needs to be from -1 to 1 in order for S of infinity to exist. And using that, what we will just do, we will drive R. Our R is going to be 8k squared divided by 16k, which is equal to 4k cubed divided by 8k square. Right? Or we can just use 2 terms, and if they cancel out, then we just don't even need to use the 3 terms. Only 2 terms are enough for us to drive R in this case, which gives us that R should be -1 to 1, then k by 2 should be -1 to 1, which will tell us that k should be -2 to 2. So for k is equal to 1.5, the series or the sequence will become this, and the R will become this. So we can have a lot of numbers between the value of -2 and 2, which can give us a sequence or a series that converges. And the S of infinity in this case is going to be, we substitute the first value, which is 16 multiplied by 1.5, which is -24. We took -1.5 as our R, and then 1 minus 1.5 is equal to this, which sums up to be this, which is approximately 13.71. Okay. Now we can do a small recap. What is our general formula for any given term at any given position in a geometric sequence? It was T of n. First term multiplied by the common ratio raised to the power of n minus 1. What is my formula for summing up this series? And what is the formula when r is from -1 to 1 and infinite sum exists? These are all the formulas that we derived and will be useful for us in the exam. You can download the whole formula list and the PDF and the lecture notes from SyntroLearn. Link is in the description.